Taking into account these differences in energy between subshells allows us to describe the distributions of electrons in an atom, or how many electrons are present in each subshell. This is called an electron configuration. Moving forward, I'll be using the terms shown here to describe the determination of these configurations. Any orbitals that are degenerate are those with equal energies. So for instance, the 2px, 2py, and 2pz orbitals are degenerate orbitals. The electron configurations we will be discussing are what are known as ground state electron configurations, which simply means that they are the lowest energy configurations of electrons possible for a given atom. The rules to determine these configurations are known as the Aufbau principle, or the building up principle. Before looking at the full set of Aufbau rules, we need to quickly introduce the notion of spin. All electrons have a property known as spin, which gives them a small magnetic field that is quantified by the so-called spin quantum number, m sub s. It's worth noting that electrons aren't literally spinning. Spin is just a property of each electron that in some ways mimics a spinning charged particle, but is ultimately its own sort of thing. The spin quantum number can be either positive 1/2, known as spin up, or negative 1/2, known as spin down. The significance of spin to electron configurations is the Pauli exclusion principle, which states that no two electrons in an atom can have the same 4 quantum numbers as each other. In other words, if they have the same values of n, l, and m sub l, they must have different spins. The rules of the Aufbau principles are shown here. Lower energy orbitals are filled up before higher energy ones, but each orbital can hold only up to 2 electrons. Any electrons in the same orbital must have opposite spins. And if 2 or more degenerate orbitals are available to be filled, we follow Hund's rule, that we add 1 electron to each degenerate orbital until all are half full. Electrons in half-filled orbitals all have the same value of their spin quantum number, which is going to be positive 1/2 or spin up. Now before we look at configurations of electrons in multi-electron atoms, I need to remind you that the subshells in these different atoms have different energies, and we even saw earlier that there was some overlap between different shells in this regard. Rather than trying to memorize where this overlap occurs, which would be nightmarish, you can use the chart shown on the right. Write out each orbital type in rows, the first row from the top for the first shell, the second row from the top for the second shell, and so on. Then, draw parallel arrows through the diagram that point down and to the left. Following the directions of these arrows, rather than just going through the rows, will give us the correct order of orbital energies without needing to know where shells overlap each other. Great, with all that in mind, let's look at how we can write the electron configuration for an atom, starting with the simplest atom of them all, hydrogen. What we're going to do is write a list of each subshell that has at least 1 electron, and indicate how many electrons are in each of these subshells using a superscript. For hydrogen, its 1 electron will go into the lowest energy orbital it can, which from the chart with the arrows on the previous slide we know is in the 1s orbital. Because there's only 1 electron, we can write a 1 superscripted to the subshell notation, and we get this, 1s1. Again, the superscript is the number of electrons in that shell, not an exponent. How about the next simplest atom, helium? Helium has 2 electrons. Since each orbital can hold 2 electrons, there is room for both of them in the 1s orbital, so we get 1s2 for helium. Let's keep going with lithium, which has 3 electrons. The first 2 electrons can be placed in the 1s orbital, but we still have 1 more electron to account for. Since there's no room left in the 1s orbital, we need to move to our next orbital, which is 2s. If we place 1 electron in the 2s orbital, we have all 3 electrons placed, so we stop at 1s2, 2s1. Make sure to always list the orbitals in order from lowest to highest energy. Let's skip ahead a few places on the periodic table and write the configuration for nitrogen, which has 7 electrons. The first 2 can go in the 1s orbital, then the next 2 in the 2s orbital. We still have 3 more to go, and the next orbital after 2s is 2p. Now remember that the 2p subshell, or any p subshell really, contains 3 separate orbitals. If each of these 3 orbitals can hold 2 electrons, that means that we can fit up to 6 electrons in the 2p subshell. However, we only have 3 more electrons to place to get to a total of 7 after filling the 2s orbital, so we will only place 3 electrons in the 2p subshell and stop. We can use orbital filling diagrams to be more specific about the electron distributions in these atoms. To do this, we use a series of lines to represent each orbital in the configuration. Then we can represent each electron with an arrow, an up arrow for spin up and a down arrow for spin down. For hydrogen, we have our 1s orbital with its 1 electron. The first electron to go in each orbital will be spin up. Next, we have helium with a 1s2 configuration. Our 1s orbital has 2 electrons. The first one is spin up, and since any 2 electrons in the same orbital have to have opposite spins, the second one will be spin down. For lithium's 1s2 to s1, we have the first 2 electrons with opposite spins in the 1s orbital, and one more in the 2s orbital. Again, this half-filled orbital will have the electron spin up. When we get to nitrogen, we need to remember Hund's rule. The placement of the 1s and 2s electrons follows straightforwardly from the previous examples, but we need to be careful about placing our 3 electrons in the 2p subshell. This subshell has 3 degenerate orbitals, so we need 3 lines. Then, Hund's rule states that we should add electrons to empty degenerate orbitals if available, only putting 2 electrons in the same orbital if no empty orbitals are available. As a result, each of the 3 electrons in nitrogen's 2p subshell go in separate p orbitals. Now, if you have to write the electron configuration for an atom with a larger number of electrons, things can get messy, or at least annoying, pretty quickly. To fix this, we can use what's called the noble gas shorthand configuration. Let's use sodium as an example. The full electron configuration is shown here. What we need to do to write it in shorthand is to find the noble gas element with the highest atomic number that is strictly lower than the atomic number of our element. In this case, the noble gas element with the highest atomic number that's less than sodium's 11 is neon, with atomic number and hence electron count of 10. We can put this noble gas chemical symbol in brackets, and this takes the place of the first 10 electrons. In this case, neon is a placeholder for the 10 electrons in 1s2, 2s2, 2p6, and the only remaining electrons in sodium's configuration is the 1 electron in the 3s orbital. So we get neon 3s1 in shorthand. Let's try this again with another element, say phosphorus. The full configuration of phosphorus is 15 electrons as shown here. The noble gas with the highest atomic number, less than 15, is still neon, so again we'll use it to replace the first 10 electrons. This gives us neon 3s2, 3p3. It's important to remember that you need to use the chart with the arrows to avoid putting orbitals in the wrong order. We'll see this in the next example. Potassium, atomic number 19, has the configuration shown here. Note that the 3p orbital is not followed by the 3d orbital, but instead by the 4s orbital. Applying that chart I showed you should enable you to determine this without the need for any weird memorization. The noble gas with the highest atomic number less than potassium's 19 is argon at 18. We can use argon, then, to replace the first 18 electrons through 3p6. This leaves us with argon 4s1. A few places to the right of potassium, we have scandium at atomic number 21. Again, argon can take the place of the first 18 electrons, and following our diagram, we can see that the remaining 3 electrons should go in the 4s orbital, followed by the 3d orbital. We stop at 3d1 because this gives us the correct total number of electrons, which is 21.